right, welcome everyone to a ConferZoom session with Professor Nancy Mahan. Today is Wednesday, April 1st, April Fool's Day, and it's 1 p.m. So we're going to start off with, I'm going to share my screen with announcements for today. All right, so the agenda for today is, we just checked it in, so it's good to hear from some of you guys what you've been doing during your quarantine time. Thanks for sharing, and I just really urge you guys to use this time as a gift. Don't squander it. The things that you've been wanting to improve on in your life, this is the time to do it, whether it's reading a book, picking up a new hobby, reaching out to friends and family. This is a great time to do things. The announcements, and then after these announcements, I'll leave space for any questions that you guys might have. We're going to go onto a new chapter now. It's on radicals. That's chapter 8 for Math 140, and that's chapter 6 for Math 130. So I hopefully you guys printed out the worksheet. If you didn't print it out, that's fine. I'll be writing the questions out, but you can find it on our file section in Canvas. And then we're going to have a 10-minute break. After the break, the group 4 presentations will be presented. I got one group's presentation. The other group, I didn't get anything from them, so hopefully you guys are ready to go. And then we'll do some student spotlights. I know Erica and Margot had mentioned last time that you guys wanted to do your spotlights. We're gonna end the class with the lecture again, and we're gonna finish it up, which will be due on Sunday. And I believe it's 18 topics. And we should be done around 3:30. So some homework that you should be aware of. Today is the exam. So some of you guys might have started, and some of you guys might be starting after this Zoom session. It's 2.5 hours. Will be available until midnight. There are 26 questions on it. Make sure you have reliable internet and you are in an undistracted space. If some of you guys are having unreliable internet, I hope you guys got the email from Long Beach City College letting you guys know of some free internet services that some companies are providing. And LBCC is also providing free Chromebooks for anyone that needs a laptop. So just letting you know, there's lots of things going on out there that's free that you guys can take a hold of. When you're doing your test, make sure you show your work on blank papers and make sure it's legible and neat, number them. And you will be turning in your work to me. The password to get in is April, and there is a lockdown browser on Alex. So once you go in, they're going to require you to install a lockdown browser, which prevents you from going onto other websites while you're on the test. Once you're done with the test, you're going to submit to me the exam itself with all your written work and to the honor pledge. And the honor pledge goes like this: I, Nancy Mahan, or what your name, pledge on my honor that I have not given or received any unauthorized assistance on this exam. And it's sign it and date it. So really it's to ask you to, based on your honor, that you are using integrity to do this exam. There's been plenty of opportunities through the quizzes, the practice exam, the homework for you to get help from people and to work with others. And this is the one time that I ask that you guys just work on your own and really assess how much you know the material. Because again, don't cheat yourself in an education. You need to know this material. The SLA is also due today. So the Math Success Center is emailing me a list of people who have done them. I haven't looked through it yet, but once I do, I'll give credit on the Alex Gradebook, so you'll see it. If you haven't done it by today yet, no worries. Make sure you go on this website, click on the schedules and follow instructions to set an appointment with them. Oops. This Sunday, so after you take the test today, after that, maybe starting tomorrow, start working on Radicals Part A, again, 18 topics, and it's due on Sunday. Okay, and keep sending me your student spotlights if you haven't done so already. Best to do it via Canvas email or through Facebook messaging. Some things to look forward to. Next week is spring break. And don't worry, I'm not one of those teachers that make you do homework during spring break. So your homework is due on Sunday, this Radicals Part A. But after Sunday, there's no more homework. So enjoy the rest of spring break. And I know it feels kind of like it's been spring break already, but enjoy it in however way you can, in whatever creative ways you can. If you want to use next week to make up on any material that you've fallen behind on, feel free to message me as soon as possible during the week to let me know what you would like me to reopen in terms of homework assignments, and I can reopen it for you. And then week 11, after spring break, we will have Zoom sessions on Monday and Wednesday again, and we'll be covering Radicals Part B. Group 5 will be presenting. And note that I switched the times. Monday we'll be meeting at 1 o'clock and Wednesday at 10 a.m. So I hope that's okay. Hopefully you can make both of them, if not minimum one. And again, they'll be recorded as well, but it's best to be part of both of them if you can. Garrett's tutoring hours are still available through this link here. He's available online. He can't help you on the exam itself though. So on anything else but the exam, he can help you with. All right, so, oh, and again, my YouTube channel with recordings and lectures. And if you guys ever have questions on a material, I could create a new video and post it up for you guys. So just feel free to ask me. Okay, and today we're gonna deal with radicals. So when we think of radical, we think of a surfer dude, or I think of a radical. Surfer dude, 18 topics. Introduction to radicals, what is a radical? How do you simplify radical? How do you add and subtract? Oh, I misspelled that, subtract radicals. And how do you multiply radicals? That's gonna be today. After spring break, we'll cover the remaining 20 topics, which is how do you rationalize radicals? How do you solve them with equations? And then we deal with complex or imaginary numbers. All right, at this point, does anyone have any questions on anything? No questions?
So the exam is open until 11:59?
Mm-hmm. Open until midnight or 11:59 tonight, yes. So it's going to be open for, once you open it, you have 2.5 hours to take the exam. I don't think you'll need all 2.5 hours, but if you need to use the entire 2.5 hours, yeah. So hopefully you've done the practice exam, so you've timed yourself, so you kind of know, okay, how to gauge your time. And remember, you have 2 opportunities to take it. The retake will be taking the questions that you missed the second time. And it's the same password, April.
And Professor, I have a question because you said that you want to see our work. Are we going to send you pictures, or well, how will we be showing you our work?
Right, so just on a piece of paper, write your work like you normally do in class, and then you would just take pictures of it and then send it to me in an email on Canvas or through Facebook. Or if you have a scanner, you can just scan it in as a PDF and just send it to me. But I think most of you guys, it's easier just taking a picture with your camera. And make sure the first picture that you take, the cover page, is the honor pledge.
Okay.
Good question.
Thank you.
Any other questions? Alrighty, without further ado, go ahead and take out the radicals worksheets that, that I put on the Canvas files. And again, if you don't have it, no worries. You could just copy down what I'm writing. But I'll be going over that worksheet, and from time to time putting you guys in breakout sessions so you guys could work with other people to practice some problems. All right, so in this chapter, we are going to be learning about radicals. So the first thing we want to discuss whenever we go into a new topic is, what is it, right? What is a radical? So before I talk about radicals, I'm going to talk about its brother or sister, what it's related to. It's related to exponents. So it has a relationship with exponents. And let's talk about exponents. This is why we learn about exponents first, and then we talk about radicals. So with exponents here, if you think about, I'm going to make a number, a table of numbers, 0, 1, 2, 3, all the way to the number 12. So all the way to the number 12. So I'll call this x. So hopefully you guys are taking notes as well. So if I squared this, if I squared everything in this column, I'll get 0 squared is 0, 1 squared is 1, 2 squared is 2 times 2 is 4, 3 squared is 3 times 3 is 9, 4 squared is 16. So let me give you a chance to go ahead and complete that list. So you guys can complete it on your sheet of paper as I complete it on mine. So what you see here are the squared numbers. We call these perfect squares. So these are what we call perfect, oops, ran out of ink. We call these perfect square numbers because they're the square of all of these integers. So those are perfect square numbers. And when we think of what are perfect cube numbers, so perfect cube numbers, we would take the first row and we would cube it. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 2 times 2 times 2 is 8, 3 cubed is 3 times 3 times 3 is 27, 4 cubed is 4 times 4 times 4 is 64, 5 cubed is 125, and then after that I don't memorize anymore, then I would need my calculator, right? So it goes on and on. So these are called perfect cube numbers. And then there's x to the 4th, then there's x to the 5th, and on. So these are exponents, right? So we're taking the exponents of each one of these integers. So that's how we do exponents. It's repeated multiplication. But now, as we talk about radicals, radicals are basically the reverse of exponents. So for an example, if I said, what is the square root of 16? And we all know, or most of us know, what's the square root of 16?
4.
4. Right. So the square root of 16 is 4. And how did you know it was 4?
Times it by itself.
Right. Because 4 times 4, if you multiply by itself, gives you 16. So what you're really doing here is so here's a square root, and again, this is the radical sign. What's invisible here is that when you have a radical sign, the invisible number here is the number 2. So even though it's not written here, it's invisible, it's always assumed to be 2, which means what number multiplied by itself 2 times will give you 16. So if you look at the square column here, what number gives you 16 is right here. Well, the 16, if I go reverse, its roots, or its root, or where it came from was from the number 4. So that's why they say, what is the square root of 16? So square, meaning what number is being squared, and the root is what did it come from? What number is being squared to give you the number 16, which is 4. So again, the square root of 16 is 4 because if you take the number 4, the root, and you square it, then you will get 16. So that's why when we say, what is the square root of, say, 121? And here, we assume that the invisible number up there is 2. So we're asking ourselves, what number being squared will give us 121? So what number being squared gives us 121? So if you look here, you see that 121 is a perfect square number, and its root, it's 11. So 11, when it's being squared, gives us 121. So that's what it means when it has these words, when we say, what is the square root of 16? So if I ask you, what is the cube root of 64?
4.
4.
Good. And how did you know it's 4?
4 cubed is 64.
Right. Since 4, the number 4, when you cube it, gives you 64. Good. And if you look at this chart on the perfect cube column, 64 is a perfect cube and its root is 4. So this radical sign is basically the reverse of exponents. They're like brothers and sisters, right? One's going one way and one's going the other way, right? So let me give us some definitions or some names to the things that we're seeing here. So here, I have N, and I'll put A here. So in general, the notations or the numbers that we see in here, this N here, so here's the cube root, the second root, etc., and then the fourth root, fifth root, that is called the index. So once I ask you, what's the index of this problem? The index is that little superscript that's written on the left side of the radical sign. And that tells you, you're asking yourself what number being cubed or squared or whatever will give you the number in the inside. And the number in the inside, or whatever's in the inside, doesn't have to be a number, it could be a letter, a polynomial, whatever. This is called the radicand. The radicand. So the radicand is that inside, and then this symbol here is called the radical sign, or the root sign. So just so you could be familiar with the words that we use for this problem, and it kind of looks like a skate with wheels on the bottom. All right, so knowing that, that is what that's what a radical is. Let's take a look at a few problems. So let's take a look at number 2. I'm going to skip around here according to what I think is best. Cube root of 8. Let me give you guys a chance to think about that problem. What is a cube root of 8? Anyone get an answer?
2.
2, right. And how did you know it was 2?
Because 2 times 2 times 2 equals 8.
Good. Since 2 times 2 times 2, or in other words, 2 cubed, is equal to 8. Right. Is everyone okay with that? Okay, so the question then is, okay, so what if you have something like the square root of 28, question 3? I have the square root of 28, so I'm going to write this invisible 2 here. So when I look at my perfect square table, is there anything that squares itself to give me 28?
No.
No, right? So I have 25 and 36. So I know the answer is going to be somewhere between 5 and 6, but I don't know what it is. So it's not a perfect square. So if it's not a perfect square, whoops. So if it's not a perfect square here, so not a perfect square. So if it's not a perfect square, what do I do? So if it's not a perfect square, what I'm going to have to do is, there's 2 ways of doing it. So I'm going to show you both ways. So the first way is the most popular way, and I think Alex teaches you that way. And then the second way is the way that I do it for all problems, easy or hard, and it works every single time. And it's my personal favorite. But I'm going to find the square root of 28 here. Okay. So since it's not a perfect square, so there's 2 ways of doing it. So the first way, so method 1 is that we rewrite the radicand as a product of a perfect square number and another number. So we rewrite the radicand as a product of a perfect square number and another number. So square root of 28. So 28, I'm going to rewrite 28 so that's a product of two numbers, and where one of the number is going to be a perfect square. What two numbers would those be? I'm sorry?
4?
4? 4 times what will give me 28?
7?
4 times 7.
Good. So I'm going to rewrite this as the square root of 4 times the square root of 7, or 4 times 7, right? 4 times 7 gives me 28. And what I could do with radicals is that you could actually split these up. Square root of 4 times square root of 7. And you don't have to write the square. It's kind of redundant because it's invisible and it should be assumed that it's there. So now that it's written, this is a perfect square and this is the leftover. The square root of 4 is
2.
2, right? Square root of 4 is 2, and then its leftover is times 2 root 7. So when you write the 2 over here and then you have a radical next to it, it's being multiplied. So you don't have to put a multiplication sign, you can just write it next to each other. So that becomes the answer. So you can again simplify this by rewriting the radicand, meaning the inside number, as a product of a perfect square number and another number. So we wrote 28 as 4 times 7, and 4 is a perfect squared, and we were able to do that. Is everyone okay with that? Any questions?
What if you use different numbers?
I'm
to get
sorry?
28? What if you use different numbers to get 28?
Okay, so what kind of different numbers would you look at?
14 and 2.
Okay, so great. So 14 and 2. So was that Anthony that was speaking?
Abraham.
Oh, Abraham, sorry. So Abraham's saying, well, 14 times 2 is 28. However, which is correct? Is 14 or 2 a perfect square? So 14 is not in here, and 2 is not in here either. So you wouldn't use that one. Because if you wrote it as 14, 2, there's really nothing you can do to simplify it. So the key thing is you want to rewrite it where it's a product of a perfect square number and it's leftover.
Okay.
Wouldn't you end up with the same answer though? 2 square root of 7?
So say again?
Would if you did 14 times 2, wouldn't you end up with 2 square root of 7 still?
Okay, so if we did 14 times 2, okay, let's entertain that. 14 times 2, okay? And then what did you do after that?
Can you break down the 14 into 7 and 2?
Okay, right. Okay, then we could break that down more into 14 is 7 times 2, and then there's this other times 2, right? And then what?
And then you bring out the 2's. So just 1 2, so it'll be 2 square root 7.
Great. So 2 times 2 is 4, square root of 4 is 2, right? It's 2 square root of 7. Great. Yeah, you could do that as well. So that requires kind of a few more steps, but you can do that. Thank you for bringing that up. Yeah, so if you did do 14 times 2, 14 and 2 are not perfect square numbers, so that's why you have to break the 14 up into another, breaking it up to all its factors, basically. And actually, that leads me to method 2. That's actually method 2 here. What you're doing is to break up the radicand to all its factors. So what I call it is create a factor, and they call it a factor tree, but I call it a factor tree trunk because it's going to look more like a tree trunk than a tree. We create a factor tree of the radicand. So create a factor tree or tree trunk of the radicand. So here, the number 28. So I'm going to take the number 28, the radicand, I'm going to break it up into its smallest factor. So what I do is I put, this is an upside down division. So I do upside down division sign, because I'm going to write all the numbers down. 28, what's the smallest factor that it can be divided by? The number 2, right? 28 is the smallest number it can be divided by is 2. And then I say, okay, what's 28 divided by 2? That gives me 14. And then what's 14? What's the smallest number could be divided by? 2. So then 14 divided by 2 gives me 7. Can I divide 7 into anything smaller besides itself? That's it, right? So now these are what we call the factors. These are the factors of 28, right? 2, 2, and 7. So you can rewrite 28 as 2 times 2 times 7. So which is kind of what we just did up here, right? And since we're taking the square root, of both sides, since we want to know what's the square root of 20, I square root both sides. Anything that appears twice, so notice that the radicand is 2, right? I'm sorry, the index is 2. So anything that appears twice is being multiplied by itself gets to be pulled out, because that's what it means to simplify a radical, right? To simplify a radical, if it's multiplied by itself twice, you get to pull it out. So here, since the 2 and the 2 are multiplied by itself twice, the index is 2, so anything that's multiplied by itself twice gets to be pulled out, and when it gets pulled out, it just becomes one number, which is just 2. And then you have a leftover of 7. So that's basically kind of what we kind of did here. It kind of loops towards here as well. So you can do either way, method 1 or method 2. Method 1 is probably better for like smaller numbers like 28, but bigger numbers where it's not as obvious, it's better to, I think for me personally, to use method 2. So either one. So I'm going to give you guys a chance right now to do question 4. What is the square root of 108? And you can use either method 1 or method 2. If it's easy for you to think of a number that multiplies to give you 108, that's a perfect square, go for it. But if you can't figure it out like me, I can't figure out, I would rather do the tree trunk. So let me give you guys a chance to do that. And in a second, I'll put you guys in breakout sessions. All right, thanks, Garrett. Okay, I'm sorry, the square root of 108, what did you end up getting again?
I got, oh, that don't see me. The 6 to the square root of 3.
6 square root of 3. Do you guys all agree?
Yes.
Yeah? And can you show us, can you explain what you did to get 6 square root of 3?
Yeah. I did the tree trunk method.
Okay.
And so I noticed that with 108, if you divide it by 2, you get 54. If you divide it again by 2, it's 27. And if you divide that by 3, it's 9. And of course, 3 times 3 is 9. And then here, I just circled the ones, or I did the ones that were perfect squares, which were 2 and 3. And there was only 1 3 left inside. And if you multiply these two, it makes 6 times 3. And then I checked by just kind of multiplying it together to see if it worked, which it did, because 6 times 6 makes 36. And if you multiply that by 3, it's 108.
Good. Okay, I'm seeing from Ivanna says thing that she can't hear anything. Can you guys hear what, was this Alexis that was speaking?
Mm-hmm.
Yeah, I can hear it as well.
Yeah, I could hear her.
So Ivanna, I'm
I
not
can
sure
hear.
what's going on with yours. Okay.
Make sure your volume's turned up.
Right. All right, great. Thank you, Alexis. So she did the tree trunk. She explained it. Everyone okay with the tree trunk?
Yes.
Can you explain it one more time?
Alexis, you want to explain it once more?
Yeah, of course. Hold on, let me. So with the tree trunk method, I just kept dividing the smallest number as the professor said, and divided 108 with 2, which made 54. And if you divide it again by 2, it gives you 27. And you can't divide 27 with 2. The smallest would be 3, which gives you 9. And 3 is a perfect square of 3 and 3. And so when I laid it out into this format and I listed all of the numbers, I noticed that was a perfect square of 2 and 3. So they would be outside, while the last 3 would remain inside as a radical. And then I would multiply these two together, since they're 2 separate numbers, and make 6. And 6 and radical 3 would be the answer. And the way I checked is I just multiplied the perfect square of 6, which is 6 and 6, and that made 36. And if you multiply it by 3, it proves that it's 108.
Great. Was that okay? Would you guys need another explanation?
No, that was fine.
Okay, cool. Yeah, so you can always check your work. I liked how Alexis said that. You could always check your work by taking the number outside, squaring it, and then multiplying by the inside to see if you get 108, right? And again, once you did all these, if it pairs twice, then you get to take it outside of the radical. So the 2's are pairs twice, so it becomes a 2. The 3 appears twice, it becomes a 3. So when you pull outside the radical, 2 times 3 is 6. And the leftover is a 3. And we'll have more opportunities to practice more of that as well. But thank you, Alexis, for showing us that.
Thank you.
All right, so next, and again, these few examples I know are not enough to do this topic justice, but that's why we have homework. Okay, now we're gonna look at variables. So what happens when you have a radical with a variable in it? So here, oops, okay, now, so let's talk about when you have a radical with a variable in it. So let's talk about square root of y to the 22nd power. So if we want to find out what is y to the 22nd power with variables, we're going to use something called the exponential and radical relationship. Relationship or definition. It's actually a definition, but I just call it a relationship because I mentioned in the beginning that radicals have a relationship with exponents. And the relationship that they have with each other is as follows. So it is, if you have, so a to the m, and then n is the index. So this is my radicand, and it's raised to some exponent, and there's its index. This is the radical expression. We can change this to its brother or sister or sibling to the exponential expression, which is this. You're going to keep a to the m exactly the same, right? Exactly as that. The only difference now is that that index is going to be a fraction, the denominator of a to the m. So a to the m is the exponent, and then the denominator of that exponent is going to be the index. Is everyone okay with that? So this is the big kahuna definition or relationship between radicals and exponential.
Serious?
I'm sorry?
He just had a mic open.
Oh, I'm sorry, did someone say something? Okay, so here, so for an example, before we do square root of y to the 22, if I had the square root of x to the 4th, right? If I want to write this, if I want to simplify this or make it look like an exponential expression, what I'm going to do is I'm going to write this as exponential, so x to the 4th. And then in that exponent, I'm going to divide it by, what number do I put in the denominator?
2.
2, right? Because the index here is 2. Since the index is 2, the denominator is 2 here. So x raised to the 4/2. Well, what's 4 divided by 2?
2.
2, right? 4 divided by 2 is 2. So the answer is x squared. And if you want to check that, if you take x squared and you multiply it, and if you square that, x squared times x squared, you get x to the 4th. And then you get the radicand. So let's take a look at this problem that we have here. The square root of y to the 22nd. Go ahead and rewrite that as an exponential.
Sorry.
No worries. Did anyone get something?
Y to the 11th power
Y to the 11th. And how did you get y to the 11th?
divided by 2.
Great. So the 22 divided by 2, you get rid of the radical, you get y to the 11th. And then you could always check your work that y to the 11th, if you square it, y to the 11th times y to the 11th, you multiply the exponents, you get y to the 22nd, which is the radicand. Is everyone okay with that?
So you just divide it every time, or would it be different?
So let me give you another example. What if I gave you to the cube power? What if I gave you w to the 27th?
Do you divide it by 3?
Mm-hmm. And what would you get?
9.
W to the 9th. And again, if you want to check that, if you put w to the 9th and you cubed it, or I'm sorry, you multiplied it by itself 3 times, w9 times w9 times 29, w to 9, you multiply the exponents, you get w to the 27th. It works out. How about if I gave you guys to the 4th power, and I gave you z to the
16.
What? I'm sorry.
16 is what I was giving you.
Okay. What would you get if we had that? 4, right? Get z to the 16 divided by 4, give us z to the 4th. Is everyone okay with that? Alrighty, so let's go ahead and combine. Actually, does anyone have questions on this? Does anyone have any questions of a scenario where it might not work so beautifully?
What if it doesn't divide perfectly?
Great, Garrett. What a great question. So what if it doesn't divide perfectly? So actually, let me look for an example. Let's look at question number 8. Can we do 15 divided by 4?
No.
No.
No, you're going to get an ugly number, right? So here, what if it doesn't divide evenly? And that's a great question. So for an example, number 8, where we have the 4th root of w to the 15th, right? If you did w 15 over 4, we're like, uh-oh. Doesn't work. So this only works when you can divide into evenly and get a nice whole number. So what you're going to do is very similar to what we did with numbers. If you can't get a perfect square number, you rewrite it so that one of them is a perfect square number and one of them isn't. So in the same way, we're going to rewrite the radicand as a product of a perfect number. I'll put a perfect variable, and it's quote unquote leftover. So what makes something a perfect variable, right? So let's look at the fourth root of w to the 15th. So what's the biggest number that I can divide by that's less than 15? What is less than, so what is less than 15 that can be divided by the index 4?
12.
12. Right, so what is less than 15 that can be divided by the index 4? And I should have said, what is the biggest number? What is the biggest number that is, so I should write, what is the biggest number that is less than 15? So the biggest number less than 15 is the number 12. So here we're writing 4th root of w to the 15th. We're writing that as w to the 12th. And so again, we need to keep the integrity of w to 15. What's the leftover then? W to the, if I have 12 here, what must I have it multiplied by to keep it as 15?
3.
3.
3, right? Because when you're doing the product rule of exponents, you can add the exponents. 12 plus 3 will give me 15. So the fourth root of w to 12, w to 12 is going to be the perfect variable, perfect exponent. So if I was to use this rule here, where you divide by the index, what does this become?
W to the third.
Great. And how did you get w to the third?
You divide 12 divided by 4.
Okay, 12 divided by 4 will give me w to the third. Great. So w to the third, that's the simplified version of this, and then it's leftover. So we can't do any we can't do anything like that, so we leave it as the fourth root of w to the third. And that becomes your final answer. So w third on the outside, you don't have to put this multiplication times sign, it's kind of redundant, but you could if you want, times the fourth root of w to the third. So it looks kind of messy and ugly, but it's the right answer. Any questions on that? So that's how you deal with something that is not a nice looking number. So let's go ahead and look at some problems here. Let's look at question number, let's look at question number 6. We'll do this one together before I have you guys do U tries. So square root of 28 times y to the 5th. So this is the radicand, and I realize it's a square root, so I put a 2 there. I'm going to break this up into 2 radicals. I'm going to have the square root of 28 times the square root of y to the 5th. So it's totally legit to do this. We can split up a radical into a product of 2 different radicals, right? Totally legit to do that. So the square root of 28, I'm going to look at this by itself. Square root of 28, is that a perfect square?
No.
No, so either you do the factor tree or you do the rewriting it as a perfect square. Let me give you guys a moment to figure that out. What's the square root of 28?
2 square root of 7.
Oh yeah, we did that already. right here. Square root of 28, we did that. 2 square root of 7. We did that in the previous problem. Alrighty then. So we had 2 square root of 7. We did that in the previous problem. Now, this one. Can I do 5 divided by 2?
No.
No, right? It's not going to be a whole number. So I'm going to rewrite this as a product of 2 radicals. For one of them, what's the biggest number I could, what's the biggest exponent I could put in here that's divisible by 2?
4.
4, good. So if I put a 4 here, then what do I need to have here as an exponent?
1 or nothing.
Right, because y to the 4th times y to the 1st gives you y to the 5th. Because of the rules of exponents, you add the exponents to get a 5. Right? You add the exponents since you're multiplying, you add the exponents. So here, what is this going to become?
Y squared.
Y squared. And how did you get y squared?
You divide 4 divided by 2.
Great. 4 divided by 2 gives you y squared. Great. So now let's go ahead and figure out what's our final answer. Our final answer, I have 2 root 7 multiplied by y squared multiplied by square root of y. Right? So I'm going to rewrite this final answer then as everything that's outside of the radical gets multiplied together. So I have a 2 and a y squared. They're outside the radical. Inside the radical, I have the 7, and then I have a y. So I have put 7y here. And I don't have to put a square root here because it's redundant. It's an invisible 2 there. So that would be your final answer. So again, you would take all the numbers or letters that are outside the radical, you multiply them together, and everything inside the radical, you multiply them together. Does anyone have any questions on this? Everyone good? Alrighty, so let's go ahead and try. I'm going to give you guys a chance to try number 7. And if you're done with 7, then try number 5. But for now, do a minimum number 7. And Garrett, can you press stop record for a second? All right, so at this point, I'm going to put you guys into breakout rooms. There'll be 4 to 5 people in each room. Garrett is a co-host, so he'll jump from room to room, and I'll jump from room to room as well. And feel free to talk to each other, ask any questions, compare your answers. Oops. Alrighty. All right, so let's take a look at this. Can someone help me out with question number, I think we're on number 7, right? What did you guys end up getting?
I got 2y to the 3rd, z to the 5th power,
Y to the
In-
3rd, Z to
sorry.
the 5th power. Go ahead.
and then radical on the inside, 6 z.
6Z. Okay, hold on one second. Okay, do you guys all agree with this? Everyone agree?
Yeah.
Does anyone have any questions on this or would like this to be worked out?
Can you work that one out, please?
Sure. Was that Alexis that gave me the answer?
Yep.
Okay, Alexis, let's start off with the problem. Can you walk through with me what you ended up doing?
Yeah, of course. So I did the tree trunk method with 24, and if you divide it by 2, you get 12. Divided by 2, you get 6. And if you divide it by 2 again, you get 3. And of course, I ordered them together, and there was one pair of 2 squared, so that made a perfect square. And inside there would be a 3 and a 2, which you could multiply together, and it would make 2 to the radical of 6. And of course, you can check that by just multiplying it all together. And so I separated that, and then I proceeded.
Does anyone have any questions on how Alexis got square root of 24 to 2 root 6? Any questions on that? Okay, go ahead, Alexis.
Okay, and then the next step is I did y to the 6th power, and because this is a square and there's no sign of it being to the 3rd or 4th in the index, I assumed it was a 2. So I divided 6 by 2, which gave me y to the 3rd power.
Okay. Everyone okay with getting y to the 3rd? Okay, go ahead.
And then last I did z to the 11th power. Sorry, it's a little blurry. And since you can't divide it by 2, I did the biggest number that was less than 11 that I could divide by 2, which was 10. And dividing that gave me 5. And of course, there's that remainder z from the 11. And so everything that I was able to get, separate, which was z to the 5th power, y to the 3rd, and 2 would be on the outside. So it'd be 2, y to the 3rd, z to the 5th, and anything that remained on the inside, which was 6, z, and that's it. It would be inside, it would be 6z.
All right. Does anyone have questions real quick about Alexis doing square root of z to the 11th and getting z 5th root z? Is everyone okay with that part? Okay, hold on. Okay, give me 1 second. Give me 1 second. Give me 1 second, buddy.
Sign up.
Okay, give me 1 second. Okay, I'm sorry about that. And then after that, she put it all together, things outside the radicals and things inside the radicals. Okay, great. Thank you, Alexis. Is that clear? Everyone okay with that? Everyone okay? Alrighty. Let me give you guys, go ahead and give you guys a chance right now to try number 5 if you haven't done so already. And I'll also give us a break as well. So optional, you could do number 5 during your break. Otherwise, you could feel free to take a break, and after the break, we'll go back and revisit that. We'll reconvene at 2:17 p.m. Okay, and then group 4 and the student spotlight people, get ready to present. And if you want to do a spotlight, please let me know on the chat. Mommy. Give me 1 second, buddy. All right, so the problem I left you guys at was square root of 24v to the 6th. So real quick, did anyone find out what the square root of 24 is?
2, 6.
Okay, 2 radical 6. Does anyone have any questions with getting square root of 24 to become 2 radical 6? All right, and how about the square root of v to the 6th? Did anyone get anything for that?
V to the 3.
Okay, v to the 3rd. Does anyone have questions with that?
No.
All right, so our final answer then, everything on the outside of the radical gets multiplied together, and everything on the inside of the radical gets multiplied together. So 2v to the 3rd, the square root of 6. Does anyone have any questions on number 5? Alrighty, so we've done questions number 1 through 8. And before we get, so we're done with the part on how to use simplify a radical. So we learned how to simplify radicals with variables, with numbers, with perfect numbers, imperfect numbers, perfect variables, and imperfect variables. We're going to move on to adding, subtracting, multiplying. But before we do that, I'm going to change the attention to be drawn to group 4 for your presentation. All right, so I'm going to go ahead and share screen right now. And I am going to,
I don't know how to work it.
You can go ahead and do it because I'm not too sure how to work it on Zoom either.
okay, I'll just put mine on then, and then just let me know when you guys want me to move forward.
All right, let me just start. Hello, everyone. My name's Abraham. I'm here today with Jessica, Esmeralda, and Ivanna, and we're going to be discussing the rules for exponents. Go to the next slide. So what is an exponent? An exponent is a quantity representing the power to which a given number or expression is to be raised, usually expressed as a raised symbol beside the number or expression. All right, there's a little example. The base, the power, and the exponent. The next slide, Esmeralda will be talking about this one.
Oh,
Can you go back to the other one? Sorry.
sorry.
The product rule. The exponent product rule is when you multiply two powers with the same base, then add the exponents. So this is an example. The base is 4 times 4, and then you could either do it the hard way, which is do it 4 to the second power, which is 4 times 4, and then do the 4 to the third power, which is 4 times 4 times 4. Or you could do it the easy way, which is the product rule, and it's you add the two exponents and you get 4 to the 5th power. Next slide. So these are some examples for you guys to do. It's v to the 3rd power and multiply that by v to the 2nd power times v to the 6th power.
When you guys get the answer, just shut it out or go ahead. You know.
V11.
And that is correct. Would you like to, well, they can't really show, right? Like what they did?
Probably not because I'm doing screen share. Yeah.
Oh, okay. And then this is the second example, which is 6v to the 2nd power times 2u to the 4th power times 3v to the 4th power and u to the 5th power. Does anybody have an answer for this one?
36 v6 u to the 9 power.
That's correct too. And then now I'm going to pass it over to Ivanna with the next slide.
So for the power rule tells us that to raise a power to a power, just multiply the exponents. So in the example that we have here, it's 5 squared times to the 3rd power. So in this case, what you would do is you would multiply the 2 and the 3, and you would get 5 to the 6th power. And then if you could go to the next slide. I have some examples here. W to the 6th power, and you would have to multiply that by 2. And then for the next one is y squared and y cubed times 4 squared. So whenever you guys have the answer to that, you can just shout it out.
W to the 12.
Yes. So for example number 1, what you would do is you would multiply the 6 and the 2 and you get 12. Does anyone have example number 2?
Would it be y20?
Yes. So for this one, you would actually add 2 and 3 to get 5. And then you'd have y to the 5th power, and 4 would still be on the outside. And you would multiply that and get 20. So then now I can pass it on to the next person.
All right, I'm gonna be going over the quotient rule. So a quotient rule is used when 2 exponents are being divided by each other, and then you subtract the powers and put the answer in the numerator or denominator, depending on where the higher power is located. Here's some examples right here. It shows you a little bit how to do it, and different options of how to do it also. On the next slide, some examples. And you guys can try this one. So it's 3z squared, 3z to the 6th power over 1z to the 5th power for the first one. And the second one is 36a to the 8th power over 4a to the 4th power. When you guys get the answer, just shout it out.
Z.
Excuse me?
3z.
It's gonna be 3z over 1. Or, yeah, 3z basically. Okay. About the second one.
9a to the 4th power.
No. Oh, shit. 1 second. I guess go to the next slide, which is going to be Jessica. She's going to be going over the negative and the 0 rule.
Hi, Professor. You can go ahead and switch to the next one. Thank you. Hi, you guys. I'm Jessica, and I'm going to be going over the negative exponent rule first. And to make a negative exponent become a positive exponent, you have to move it from the numerator to the denominator or vice versa. And here's some little examples at the bottom that I wrote out. So you would flip the a and the negative m and put a 1 over it to make it positive. And the same thing with the bottom half, you would just flip it, so the reverse. Can you go ahead and move to the next slide, please? So this is like a simple little example that I picked out. You guys, it might be familiar to some of you guys. So if you finish it, just go ahead and shout it out, and then I'll let you know if it's the correct answer. Did anyone figure this one out yet? If not, I mean, I have the answer. So basically all you have to do is flip the sign. So it's just the opposite. So not the flip everything. So it's 7-3 over W2 for that answer. It's pretty simple. I feel like these two rules are the easiest ones. I know these can get a lot more complicated, but can you go ahead and flip to the next one, Professor? Thank you. And then this is my favorite rule, super easy. So any number to the 0 power will always equal to 1. And if you flip to the next slide, there's an example to do as well. And then if you guys do figure it out, just let me know. And if not, I'll go ahead and just give the answers out.
Two.
What happened?
For the first one, wouldn't it be -1?
Yeah, pretty much, yeah.
And then the second one, 1.
Yeah. So you got those all correct. The -1 and 1. I feel like these ones are like the easiest out of all the rules to do. So that's the end of our presentations. Did anyone have like any questions or feedback? Professor, did you have any questions or feedback for us? Oh, I can't hear you.
Hi, can you hear me now?
Yeah.
Okay, I thought that was great. I loved how you guys reviewed all the rules for exponents, and that's something that we're always going to be using even in this section. And I liked how each one of you guys owned one part of the rule and then did an example for the class. I know it's hard to get participation over Zoom sometimes. Now you guys know how I feel. But I loved it, and I loved the presentation. It was very organized, and yeah, good job. I'm really glad you guys did a review of exponents. We need that.
Thank you.
Great job. The other group 4, hey. The other group 4, are you guys there?
Yes.
Yeah.
Okay, and who's in this group right now? In this other group 4?
Yes. This is Alexis and Suzette.
Alexis and Suzette?
Mm-hmm.
Okay, do you guys have a screen that you guys want to share?
I had emailed you the PDF because I don't really know how to screen share.
Okay, so it's on, let me,
It should be on Canvas.
it's on Canvas? All right. Let me go look for it. So it's on Canvas, you said?
Mm-hmm.
And you emailed it to me.
Should be the second one there that says Alexis.
Oh, group 4. Oh, you just did it right now. Got it. All right. Alexis, Suzette, and it's just for you as well? Or is it just you two?
It's just us.
Okay, you guys are on like Donkey Kong.
Awesome. Okay, so today our presentation is on mixture problems with decimals. To the next slide, please.
How do you do next slide on? Oh, okay.
You can just, yeah. So what is a mixture problem? A mixture problem is a word problem explaining two amounts, usually in the form of solutions, as being combined into a singular amount. Often mixture problems include two liquid amounts along with their percentage of concentration, though this is not exclusive to all mixture problems. This will be the one that we're focusing on for the first example. Next slide, please. Now for the example, we're going to have two examples in the presentation of two different methods to do a mixture problem. And the first example is the one that we learned in class, or the one that we mainly do in class. For this one, a chemist needs 5 liters of 50% salt solution. All she has available is a 20% salt solution and a 70% salt solution. How many liters of each of the two solutions should she mix to obtain her desired solution? Now, there are two equations that you need to remember in order to get the correct amount and percentage, and that would be the ones that we focus are amount 1 plus amount 2 equals amount 3, and amount 1 multiplied by the percentage it's given plus the amount 2 multiplied by its percentage equaling amount 3 to that percentage. These two are going to be the main ones that we focus on, and they're going to be color coded so nobody gets mixed up, hopefully. Next slide, please. So we're going to focus on, we will use A to represent the unknown, that is amount 1, and B as the unknown for amount 2. And for C, it's just going to be 5 liters because we already have a known sum for it. So it's going to look like A plus B equals 5. Now, we already know the obvious that amount 1 and amount 2, of course, makes amount 3. So that gives us kind of an understanding of what we need to start with. And then for the next, we're going to multiply each variable with their percentage, which will be A times 20% plus B times 70% and 5 times 50%. Now, what was it? Sorry. We are, oh, here we go. Thank you. Now we are aware of the amount of solution 1, we are unaware of the amount of solution 1 and 2, but because we know what solution, the amount of 3 is, we're going to be able to multiply that one first. Now the easiest way to do this is just to turn the percentages into decimals. Does anyone remember how to do that?
Move it 2 times to the left.
Yes, and divide, by 100, yes. And so, next slide, please, thank you. In order to multiply the percentage to amounts, we convert them into decimals. And because we already know the sum, which is 5, we can multiply it by 0.50, which is 2.5. And then the next step is to go back to the first equation so we can rewrite it. And the reason why we do this is so we can plug it into one of the unknown variables to get an answer of one of the amounts. So the one I chose was A, that I wanted the variable to be known. So I subtracted B to both sides, eliminated B on one side, and I got A equals C minus B. Now that we have that, we get to plug it into the into the equation where A turns into 2.5 minus B times B times 0.70, and it's times 0.20 since that percentage is still there, is still multiplied to A, plus B times 0.70 equals 2.5. Now we distribute we distribute 0.20, into that equation, or that little parentheses, and we get 0.5 minus B times 14. And now that we have that, we can combine like terms, which would be B.14 and B.70. And when you do that, you get 0.5 plus 0.56B equals 25. And now that we have that, we can, now isolate B. So we are going to, subtract 0.5 to the other side, and we get 56 0.56 times b equals 2.0. And then we, of course, divide 0.56 and we get 3.6. And now having that amount, we now have we now have a second amount, which is b. And now that we have that, we can plug it in to the first equation that we just rewrote, which is a equals c minus b. And you get a equals 2.5 minus 36. 3.6, and a equals negative 1.1. So now that we have both solutions, we can check our work and go back to the original first equation, which is a plus b equals c. And you can see that negative 1.1 plus 3.6 equals 2.5. So we now have both amounts. And now Suzette can do the second example.
Okay, the second example is more with money, which is still decimals. A candy company sells packages of milk chocolate bars for $1.50 per pound, and a package of dark chocolate bars for $1.75 per pound. The company wants to make a package of mixed candy bars that include milk and dark chocolate that will sell for $1.60 per pound. If the candy company uses 15 pounds of dark chocolate bars, how many pounds of milk chocolate bars do they need to use to get the desired mix? Next slide. In order to find out how many pounds of milk chocolate bars are needed for the mixture, we need to make a chart in order to figure out the equations for milk, dark, and mixed chocolate bars. First, we have to let x equal the number of pounds of milk chocolate bars. Now we insert the number of pounds per cost per pound and the total cost of each kind. So we made a chart, and then the number of pounds go x, because we don't know how many pounds of chocolate bars that we need yet. And then we know the amount of dark chocolate bars, and then we put x plus 15 because we're still trying to figure out the amount of milk chocolate bars. And then we know the cost for each pound, and then we just multiply each to make each equation. Now we add the milk and dark chocolate equations and equal them to the mixture equation. So here we added the first two equations, then we equal them to the mixture equation. Then you multiply 100 to each side so we can remove the decimals. So we get whole numbers, and then we'd multiply 1/5 to reduce it so we don't have to do more. So it's a smaller number. And then for the final answer, we got 22.5 pounds of milk chocolate bars. These kinds of problems are applied in the real world when figuring out the amounts of a product you're either mixing and or adding. You'll mainly see that foods and liquids are used as examples in mixing problems, as well as quantities and percentages / decimals when figuring out the different amounts. That's it.
Alrighty. Great job doing problems on mixtures. Those are one of the hardest problems for students with word problems. So I'm glad you showed two examples. I love the charts and the explanations. Anyone have any comments or questions for this group or for the other group? All right. Well, without further ado, I know I said I was going to leave some time for student spotlights, but I think I'm going to keep going forward with the lecture because I see that we have about 40 minutes left, and I want to make sure that we get through as much of the lecture as possible. So I'll hold off on the other student spotlights until later on. So we have until the end of the semester to finish the student spotlights. But because we had 2 groups going today, it kind of ate into the time. But so those who I said that you guys can do your student spotlights, let's count and do that next time. All right, so now let's go ahead and looking at, now that we know how to simplify radicals, the next thing is we want to learn how to add and subtract and then multiply. And then next week after spring break, we'll learn how to divide radicals, solve equations with radicals. That's how we always end up every single chapter. So I'm going to go ahead and switch screens real quick. And can you guys see this? Okay, I think I'm putting it on the wrong one. Spotlight video, that's what I meant to do. All right. Hannah, can you please close that for me? Can you please close the door? Just so that I need to focus. Thank you. Yes. All right, so question number 9 and onward is about how do you add and subtract radicals. So here it's going to be from number 9 until number 12. So I'm going to write here, number 9 to 12 is about adding and subtracting radicals. So here, when we talk about adding or subtracting anything, if you guys remember, we always need like terms. So if you recall, when we did fractions, can you guys all see this?
Yes.
Yeah, okay, I just want to make sure you guys can see this. So if you can recall, when we did fractions, if we had 3/4 plus 7/4, right, we needed to have the same denominator, and we kept the animal or the denominator the same, and we just added the top. When we talked about polynomials, when I had, say, 3x² plus 4x², if they were the same animal, you keep the animal the same, and then you just add the coefficients. So, and even in terms of English, when I said 3 cats plus 4 cats, right, the animal never changes. You just add the coefficients to get 7 cats. So this is the same thing now with radicals. So in order to combine like radicals must have the same radicand. So radicand is the things inside the radical. So same radicand and same index in order to combine. So again, you need to have the like radicals in order to combine. So for an example, if I had square root of 4x plus 7 square root of 4x, the first thing I want to, that's a 4. So the first thing I want to check is, are these the same animals? And the answer is yes, because this is the square root of 4x and the square root of 4x. They're the same animals. Because they're the same animals, so same animals, then I can add the coefficients. Add the coefficients. So just like here, 3 cats plus 4 cats, if they're the same animal, you keep the animal the same, but you add the numbers in front of them. So the animals are going to stay the same. So we still have square root of 4x. But the thing that changes is the number in front. So what's the number in front of square root of 4x here?
1.
Yeah, just 1. right? The number in front of the square root of 4x is just 1. So 1 plus 7 will be 8. So that's what it means to add or subtract radicals. The first thing you have to check is to make sure that they are the same or like radicals. So like radicals have the same index and the same radicand, and then all you do is you just add the coefficient in front. So that being said, so what happens then if you have unlike? What if you have unlike radicals? So if we look at here, number 9, square root of 75 plus 3 square root of 12. Are these the same radicals or like radicals?
Nah.
No, right? They're not the same. This is root 75 and root 12. These are not like radicals. So what you're going to have to do, so in this problem, square root of 75 plus 3 radical 12, we can say not like radicals. So we cannot add them as is. We can't combine them as is. But what we can do is notice that we can simplify each radical. So the thing is, they might be disguised as like radicals. So root 75, can I simplify this? And this is why we spent so much time on simplifying. Square root of 75, go ahead and simplify square root of 75.
5 square root of 3.
5 square root of 3, and how did you get 5 square root of 3, Anthony?
I factored out 75 to 25 and 3.
Okay.
And then the 25 to 2, it will be 5. So 5 square root of 3.
Perfect. Is everyone okay with 5 root 3? So again, you could do the tree trunk method, or you could rewrite it as a product of a perfect square and its leftover. Everyone okay? Okay, now let's look at 3 root 12. Go ahead and try simplifying 3 root 12. Anyone get an answer?
You got the 6 to the square root of 3.
Okay, and how did you get 6 to the square root of 3?
Tree trunk method. I divided 12 with 2 and 6, and then the 6 with 2 and 3, and you get a perfect square of 2. And you just multiply that with the 3 that is outside already, and you get 6 to the square root of 3.
Great. Is everyone okay with what Alexis just did? Any questions? Alrighty. So notice that the root 75 becomes 5 root 3. 3 root 12 became 6 root 3. There's an adding sign between them. And what do you know? Are these like radicals? Yes, right? They both have a root 3. So what do you get as an answer?
11 root 3.
Great. 11 root 3. Right? Because we added the 5 and the 6, and then we left the radicand the same. Anyone have any questions for me on this? All right. So again, sometimes we could start off with adding radicals, and they don't look like radicals. So you have to do something to make it look like radicals, and that's by simplifying it first. So I'm going to give you guys a chance right now to go ahead and try this with question number 10. So I'll give you some time to work on this. So as is, they do not look like radicals. But see if you can simplify it and if they're like radicals, go ahead and combine them. And in a second, I'll put you guys in breakout sessions to compare your answers.
How come you're not doing at work?
Alrighty. So we're gonna go back to, sorry, where am I at? We're gonna go back to this problem, and I've asked Abraham to help solve this problem for us. Can you guys see this on there? You guys can see it? Okay. All right, so question 10, what did you do, Abraham?
I got, so right there, 5 square root of 75. We already solved it before, so I just plugged it in. So 5 times 5 is 25. It's gonna be 25 root 3.
25 root 3. Is
For that
everyone
one?
okay with getting that? Any questions?
Yes, why did he times it by 2? Oh, I mean, why did he put 5 times 5 instead of to get 25?
Because it was I reduced it to I did the tree trunk method,
Mhm.
and I got the 5 left over, so I just times it with the other 5 right there.
Oh, that's right. Okay.
Yeah. And for the next one, on 12.
So this is 5 root 3 for square root of 75, and then you multiply the 5 times that 5 right there to get 25, right?
Yeah.
Okay, go ahead.
And the next one I got minus 2 root 3.
Everyone okay with that?
Yeah.
Okay.
And then I just did the math right there, which I got 23 root 3 plus 13 root 3. And my answer was 36 root 3.
Alrighty. Does anyone have any questions for Abraham? Any questions at all? All right, nice work, Abraham. Thank you. So next up, we're going to go ahead and look at a few harder problems now. Now let's try adding and subtracting with variables in them, right? So when we have variables, how do we do these problems? So let me do, let me see. I'll do number 11 with you guys. So here at number 11, when I look at this problem here, and I look this minus this, I notice, okay, they're not the same radicand, so I can't add them as is. So before I do that, I'm going to see if I can simplify each one of these. So let's look at square root of 48, square root of 48y. So when I do that on the side here, the square root of 48, what's the square root of 48? Does anyone know?
It is, sorry, square root of 48 is 4 to the 3rd power.
4 to the 3rd power? So
Yes.
you're probably using the tree trunk method, right, Alexis? Okay.
Yes.
So let's do 48 divided. What's the smallest it divides by?
2.
Right. So that's going to be 24 divided by 2. I get 12. Divided by 2, I get 6. Divided by 2 again, I get 3. So that's why you said 2 to the 4th power, right? So since it's the square root of 48, what appears twice? The 2 and the 2, right? These two appear twice, so they get to be taken outside of the radical. When this is taken out of the radical, it becomes a 2, and this takes out of the radical, it becomes a 2 as well. So 2 times 2 is 4, and then what's left over is the 3. Do you guys have any questions on that? 4 root 3. So right now, I have the 4 root 3 for square root of 48. So I'm going to multiply the 4 by what's outside already. So I get 16, because 4 times 4 is 16. I have the y squared outside. Inside the radical, I have the 3, and then what was in here was the y. So 3y. Any questions on that? I multiplied the 4 inside, and then the 3 was multiplied by the y that was still left over inside. Everyone okay? Minus square root of 12. what's the square root of 12? I think we've done it over and over, 2 root 3, right? We've been doing that over and over in all of these problems. So 12 is 2 root 3. So I have 2 root 3. That's 12. And here's y to the 5th. So y to the 5th, the square root of y to the 5th, I could rewrite, since 5 cannot divide by 2, I'm going to rewrite this as y to the 4th times y to the 1st. Because 4 plus 1 gives me 5. So if I do 4 divided by 2, then I could pull this outside the radical and I get y squared. Because 4 divided by 2 is just y squared. And the leftover is the square root of y. So square root of y fifth became y squared square root of y. Is everyone okay with that? So here the y squared goes outside the radical. And then the y stays inside the radical. So I'm left with this. Does anyone have any questions at this point? All right, so now that I'm left with this, I'm going to ask myself, are these like radicals? And the answer is yes, because I have square root of 3y and square root of 3y. These are the same animals or like radicals, so I can combine these two. So since they're the same animals, I leave the animal the same, square root of 3y, and then I add or subtract the coefficient. 16y squared minus 2y squared. Well, 16y squared minus 2y squared gives me 14y squared. So this becomes my final answer, 14y squared square root 3y. Does anyone have any questions? Alrighty. Without further ado, let's go ahead and have you guys try. Go ahead and you try for number 12. So again, I'll leave you guys with a few minutes to work on this, and then I'll put you guys in breakout sessions. Okay, oops, I forgot to record this earlier. So all in all, question number 12, after we do all that, we end up getting negative 41by square root of 2y. Are there any other questions? All right, great job, you guys, on working on that. I see that we have 5 minutes left, so I do want to honor the time. So that was all the way up to question number 12. Now, the last 6 questions or so, all the way from 13 to 18 are about multiplying radicals. So I'm going to do a quick lesson on multiplying radicals, and I'll just do one problem. And then if you guys have more questions, I could stay online with you guys. And or if you want, just let me know and I could do a video for you guys as well. So here, with multiplying radicals, when you multiply radicals, the nice thing, remember when we talk about multiplying radicals, you don't have to have anything the same. You don't have to have like terms. So you just multiply the insides of the radicals together, and then multiply the outsides of the radicals together. Sorry, my writing's getting messier. So here, if I look at number 13, I have 4 radical 75 times radical 12. We do not need like radicals, right, to combine them. So multiplication just is a lot simpler. So what you could do is you just have 4 in the outside. So the outside is a 1. So if I multiply the outside, I get 4. If I multiply the inside, 75 times 12. 75 times 12 is a really big number. So what I can do first is, instead of multiplying these big numbers, is to simplify each one first so I can work with smaller numbers. So if I look at square root of 75, we know that square root of 75, I think we did that earlier, was 5 root 2, right? We did that problem earlier. Square root of 75 is 5.
3. 5 root 3.
5 root 3?
Yeah.
5 root 3. Is that right? Yes.
Okay.
Right. Thank you. Thank you for the correction. 5 root 3. So here, 5 and the 4 on the outside gives me 20 root 3 times square root of 12. What's the square root of 12? I think we did that a couple of times as well.
2 root 3.
2 root 3. Good. So at this point, we're getting faster and better at these, right? So now I'm going to just multiply them through. So the outsides multiply together. So here, I'm not going to do that anymore. So multiply the outside together, I get 40. If multiply the inside together, root 3 times root 3 is root 9. Well, what's the square root of root 9?
3.
Just 3. So 40 times 3 gives me 120. So the idea of radicals, multiplying radicals, is actually pretty simple. You multiply the outsides together and you multiply the insides together. And if they're pretty big numbers, and if you get intimidated looking at big numbers and you don't want to multiply 75 times 12 and then having to simplify that, you can simplify it first, simplify everything first, and then multiply afterwards. So I'll do one more problem just so you guys can get a sense of this. I'll do number 15. And if you look at 16 and 17, all you're going to be doing is you're going to be just multiplying it through, right? Foiling or doing things that you've done before. So there's nothing that changes with it. You just need to be careful with the radicals. Question 15, I'll do that real quick. Radical times a radical. 3 times 6 will give me radical 18. X times x to the 6. If I multiply those together, I get x to the 7. Y fifth times y to the 8th. If I multiply those together, I get y to the 13th by the power rule or the product rule of exponents that we saw in the group presentation. And then I can simplify it. So 18, when I simplify 18, that gives me square root of 9 times square root of 2, which is the same thing as 3 root 2. So put 3 root 2 here. X to the 7th, I could rewrite that as x to the 6th times x to the 1st. 6 is the highest exponent that's less than 7 that can be divided evenly with the number 2. So that becomes 6 divided by 2 is x third. It's leftover is just x. I know I'm going a little bit fast, I'm sorry. And then y to the 13th. Y to the 13th can be rewritten as y to the 12th times y to the 1st, because y to the 12th is the largest number that's less than 13 that can be divided by 2 evenly. So that gives me 12 divided by 2 is y to the 6th square root of y. So I know I'm going through that a little bit fast just for the sake of time. So now all of these three, I'm going to multiply them together. Things on the outside stays together. So I end up getting 3x cubed y to the 6th square root of 2xy. 2xy stays in its radical. And that becomes the final answer. Any questions on that? All right, so numbers 16, 17, and 18 really are just multiplying through, right? And I would recommend creating charts so that it's easier to see. Say 5 minus 2 root 10, and then multiplying that with 2 root 5 times the negative 1. If you guys remember this chart that I created before, when multiplying two things, it'll make it easier for you to organize your work. We can organize it together and then add them all up, just as you would do when you FOIL. So nothing changes, just be careful with working with radicals. Alrighty. Well, that concludes our session for today. Remember that the homework for this section, 18 problems, are due on Sunday by midnight. Your exam is due tonight. Remember to send me your exam work and the honor pledge and the DLAs. If you haven't done so, make sure you make an appointment with the Math Success Center. Other than that, if you guys have any questions on anything, I'll stay on for another 10-15 minutes. And if you guys ever want me to do a video on a topic that you're stuck on, You could use this worksheet as a guide or say, hey, can you do this problem or this number? And I'll be happy to create a video for you. Other than that, thank you so much for joining, and I'll see you guys another time. And best of luck to you guys.
I have a question about the exam work we have to give you. We upload it through Canvas or we email it?
You can upload it through, you could just email it to me through Canvas. So go on Canvas and send it to me as a message.
Okay.
Any other questions?
I had a question about the DLAs.
Okay.
Because I got mine done today, but the tutor that was helping me, she said that they're not really sure like how they're doing it. You know how before we'll have the stamp and we'll show you that?
Mm-hmm.
Have they gotten back to you about how they're gonna do it?
Oh, okay. They just basically send me a list of people who participated.
Yeah.
So once I get that list,
okay.
I'll update it on, you'll see it updated on Alex probably in the next few days.
The tutor should be keeping track of the students that they have helped and done DLAs for, and then giving that list to Sunday, and then she's going to forward that to the teachers.
Oh, okay, okay. I get it.
So yeah, as long as the tutor took down your name, you should be okay.
Yeah, okay. Thank you.
Mm-hmm. Anybody else?
Professor, for my exam, it's still not letting me open it.
Okay, so on the exam for Alex, you need to be able to have the lockdown browser downloaded. Were you able to do that, Abraham?
I'm trying to right now.
And what is it giving you?
The same thing. It says downloaded, but the same thing happens. The same thing.
Is anyone else having problems like Abraham accessing the exam? Did you try a different browser?
I don't know if I could because I got a Chromebook, so.
I'm sorry, can you say again?
I don't know if I could because I got a Chromebook. I don't know if it lets me use no browser.
You know what? If after this, I'll go ahead and go into Alex and cancel the lockdown mode then, so that you won't have a problem with that.
Oh, if you can, you think I could do it by hand maybe? If you have the test questions with you, you could just send me the pictures maybe.
Right.
I don't know.
Well, you know what? Let me go ahead and let me stop the recording right now.